This is the first in a series of videos regarding heat load and heat load calculations. Heat load is an important concept for any HVAC technician to have because you have to understand why and how the heat is transferred in and out of a building. In order to properly install a new system, you have to totally understand how to size the system you're installing, because a system that is too large will actually not dehumidify and cause you more problems than a system that is too small. So let's start off with an introduction to the heat transfer process. Okay, we have to remember the purpose of heating systems is to control the environment to a set point and then to replace heat lost. Okay, so in other words, we have a thermostat on the wall and we want to control our environment to that point of the thermostat on the wall. Okay, what causes our heat loss? It's a temperature difference. Outside is cold, inside is hot. So the temperature difference is what the cause of the heat loss. Okay, so let's talk about what heat loss is, what causes heat loss, how heat loss is measured, and what affects the rate of heat loss. There's two different types of heat loss. Okay, it's transmission loss and infiltration loss. The total heat loss of a structure combines these two losses. Transmission loss is heat that is transferred through the walls, glass, ceiling, floor, or any other surface. Any surface that is connecting or between indoor and outdoor environment, or hot and cold. Okay, heat is lost through all building surfaces that separated the heated space from an unheated space. Infiltration loss is the energy that's required to warm the outdoor air, if it's cold, that's leaking in through cracks and crevices. Okay, around every single door, window, or through open doors or windows, and through the porous building materials. Okay, feel around a cold an electrical outlet on an outside wall on a cold day. A lot of times you'll feel cool air. Okay, that's actually heat leaving the building. Okay, that's infiltration loss. Okay, so talking about transmission loss, okay, we have the human body, it's a heat source. Okay, we wear warm coats, scarves, gloves, okay, in the winter, and shorts and sandals in the summer, because you are either losing or gaining heat. Okay, the human body creates heat. If the air around your body is colder than your body temperature, the heat leaves your body, because heat will always go from a warm to a cold area. Okay, the human body as a heat source, it generates heat. The heat activity engaged changes the comfort level in the conditioned environment. For example, a basketball player in a gym who's being very, very active is going to be putting off more heat, is going to have a greater temperature difference to the surrounding air than a researcher in a library does. An office worker is estimated to give off 500 BTUs per hour. Now remember, BTU is British thermal unit. Okay, that office worker will give off 500 BTUs per hour because they're relatively sedentary. The human body at rest produces the same heat as a 100-watt light bulb. Okay, now heat always goes to a cooler place than your body, because heat will always flow from a hotter to a cooler environment, and that's not always desirable. It leaves at a rate relative to the temperature difference between your body and the surrounding area. Okay, now if the temperature difference is too great, you're going to feel cold. And if the temperature difference is really great and you don't protect yourself, that's where hypothermia comes in. So let's talk about winter in the north. Okay, it's cold. You have no protection, and any heat your body generates is transferred immediately to the surrounding area. Now, if you build a little box about around yourself, it provides some insulation from the outside. The heat from your body slowly warms the air in the space. But since Mother Nature hates imbalance, and since you don't have enough insulation to sufficiently slow down the heat transfer leaves your body faster than your body's ability to generate it. You add heat to your space, the temperature starts to go up. Okay? Now here comes nature again. This time she just steals it a little faster at a faster rate. Notice the outdoor temperature is dropping. That's the number right here. Okay? Now you can build a fire. Okay? So you'll overcome the rate at which nature can steal it. The cost of a bigger fire starts to hit the pocketbook. So what can we do? We have to realize that outdated construction methods were based on cheap fuel. One overpowered heat loss with a huge furnace, resulting in larger quantities of fuel being used. When the energy costs going up, this method isn't the smartest design. We're left with many legacy buildings which leak like sieves and have energy-devouring, oversized heat sources. That's what this whole thing is important about. Using appropriate combination of insulation materials and heat sources, we can finally achieve the desired temperature. The point of maximizing the R value, that's the insulation value of the shell, is to slow down nature's tendency to equalize imbalances. If you can retain the heat, then you can reach your set point without having to have unnecessarily large heat sources. The more insulation, the slower the heat loss, and the smaller the heat source required at design temperature. When the BTUs in equals the BTUs out, the temperature remains constant. So let's look at a couple examples of heat loss. So you set a hot cup of coffee on a desk in a comfortable room. Come back in a few hours. Is it still as hot as you left? Why not? What happened to the hot? Another example. Set a glass of water with lots of ice on a desk in a comfortable room. Come back in a few hours. Is it still as cold as you left? Why not? What happened to the cold? As the temperature of the contents get closer to the room temperature, the rate of heat transfer slows down. The rate of transfer from a hot to cold is relative to the temperature difference. As the two temperatures get close to the same difference, which is known as delta T, the less the transfer rate, therefore the rate slows down. 4 things we have to remember. Hot always goes to cold. Always. Hot goes to cold at different rates relative to the temperature difference. So in this slide, we see the hot and the cold is both at 70 degrees. There's going to be no movement of heat back and forth between the two environments. Okay, when inside and outside temperatures are the same, there's no heat transfer. That's called thermal equilibrium. In this case, the red and blue ping pong ball is just as equal. Now, the outside temperature drops. Our hot environment is 70 degrees, cold is 35. Our little ping pong ball, or heat, is going to move from the hot to the cold environment. The outside temperature drops even further. We now have a temperature difference of 70 to 0. That's a delta T of 70. Heat is going to transfer much faster from the hot to the cold environment. Hot goes to cold. Hot goes to cold at a rate relative to the temperature difference. The third thing we have to remember is radiant heat goes to an infinite number of directions from the source. Okay, heat is lazy. It's going to always follow the line of least resistance. Okay, Radiant heat will go at an infinite number of directions from the source. Radiant heat, sunlight. The sunlight, the heat that's in the sun, is going to go out in all directions. Okay, it doesn't just go up, as in misleading statement, heat rises. We'll talk more about that. So then we add the heat is lazy. It will follow the line of least resistance. So again, 4 things to remember about heat transfer. Hot goes to cold. Hot goes to cold at a rate relative to the temperature difference. Radiant heat goes from an infinite number of directions from the source. And heat is lazy. It's always going to follow the line of least resistance. So that's an introduction to our topic of heat calculations. We're going to get into load calculations, but we still have to go through a few things like methods of heat transfer and a few other topics. So that's it for part 1.